This is week 9. We're going to have a bonus problem of the week, calculating with residues, because people have been having some problems in working with residues. So I'm going to show you how you integrate with residues in the world of the complex. So we're going to start by looking at trig substitutions on the unit circle. We're going to carefully go over how we convert these to integrals from an interval, say 0 to pi or 0 to 2 pi, onto an integral over the unit circle, and then we'll give a general strategy for how you evaluate these integrals themselves. So consider an integral of the form integral from 0 to pi or 0 to 2 pi d theta 1 over a minus cosine theta. In reality, you can think of it as sort of any function of cosine theta and sine theta. We can handle all of them this way, although depending upon how complicated the function is, it can get more and more complicated. So we're looking in this case at a particularly simple example, but it shows the general picture for how we are going to proceed in evaluating this type of integral. We have to pick a bigger than 1 for this integral to be well defined, otherwise the cosine theta would cancel out the a at some point, and we would have a singularity in the integral itself, and that singularity is not one that you can integrate over. So at this point, the integral is over a finite line segment, and that line segment is the line segment in terms of the angle. To convert it to an integral over the unit circle, we have to introduce the complex number z equals e to the I theta, and you can immediately verify by looking at z times z complex conjugate that the mod z squared is equal to 1. So it lies on the unit circle, and as theta increases, we go around the circle in a counterclockwise direction. Now, what about the cosine? I need to write it as an analytic function. Well, there's a number of different ways I can write the cosine. It's the real part of z, or it is 1/2 z plus the complex conjugate of z, or it is 1/2 z plus 1 over z if I'm on the unit circle. And it's only that last form that involves analytic functions, so that's actually the form that we have to use. If you had a sine, it would be 1 over 2i z minus 1 over z. That would be the expression for the sine function. And of course, if I had tangent, I would take the cosine expression divided by, or the sine expression divided by the cosine expression, and so forth. Okay, so when we make the substitution, we're going to have to recognize that dz equals I e to the I theta d theta, which is equal to Iz d theta, so d theta is equal to dz over Iz, and that then allows me to write this integral as dz over Iz, remember that's d theta, times 1 over a minus 1/2 z plus 1 over z, that's the cosine theta, and now I factor a 1/2 out of that denominator, and I multiply the denominator by a z, so I get 2 over I times 1 over 2az minus z squared minus 1, and I'm going to factor a minus sign out of that, and so I'm going to get a 2i times the integral around the unit circle, dz, 1 over z squared minus 2az plus 1. Alright, we're getting close. Now we have an integral that goes over the unit circle. We know the answer will be 2 pi I times the sum of the residues that lie inside the unit circle. So we have to find where are the poles of that integrand. Now remember, a pole is where the integrand goes to infinity, and this occurs when the denominator vanishes, but the denominator is a quadratic equation in z. Hence, we can find where it vanishes by finding the roots, which we're going to call z plus minus, or another way of saying it is that we're going to rewrite z squared minus 2az plus 1 as z minus z plus times z minus z minus. And in order to determine z plus minus, we have to use the quadratic formula, and by plugging in, we immediately find z plus minus is a plus or minus the square root of a squared minus 1. Now we're going to use another little trick. You've seen this before, but I want to make sure you all have seen it carefully because it's a really cool trick. We're going to expand the right-hand side of the factorization where we wrote z squared minus 2az plus 1 equals z minus z plus times z minus z minus. We're going to expand that out. We're going to get z squared minus the quantity z plus z minus times z plus z minus. And because that has to equal z squared minus 2az plus 1, it immediately tells us that 2a is equal to z plus plus z minus, and 1 is equal to z plus times z minus. And it's the second equation that we care about because that tells us the modulus of z plus is equal to 1 over the modulus of z minus. Hence, if one root lies inside the unit circle, the other must be outside. This tells us there's only one pole inside the unit circle. All right, how do we find which root is inside and which is outside? Well, recall we have z plus minus is a plus or minus the square root of a squared minus 1, and we have a bigger than 1. So that square root is going to be a number that is smaller in magnitude than a. So if I add them together, I'm going to get something that's on the order of 2a. It might be a little bit less than 2a, but it's close to 2a. But remember, a was bigger than 1, so that's outside the unit circle. If I use the minus sign, I'm taking a and subtracting a number that is close to a, but slightly different. That is going to give me a root that lies inside the unit circle. All right, so we know that z minus is the root that lies inside the circle, unit circle. How do we find its residue? Well, we have to recall what the definition of a residue is. I take a function f of z at the point z0, and then the residue is going to be the limit as z approaches z0 of z minus z0 times f of z, because the residue is the coefficient of the 1 over z minus z0 term. So in our case, what we're going to find is the residue is the limit z approaches z minus, because z minus is where the pole is located, z minus times the integrand, which is 1 over z plus times z minus. You can see the z minus terms are going to cancel. I'm left with, and I have to evaluate it at z goes to z minus, so I'm left with 1 over z minus z plus. And when I work that out, I get minus 2 times the square root of a squared minus 1. So that's my residue. And we now have to put this together to find the integral itself. So remember, our integral at the top has got a factor of 2i. I have to multiply by 2 pi I because it's 2 pi I times the residues. And then I have to recognize the residue was minus 1 times 1 over 2 square root of a squared minus 1. And when all the dust settles, you can see that I get 2 pi over the square root of a squared minus 1. So this is the strategy that we use to convert a general trig integral that involves some rational function of cosines and sines into a integral that involves a polynomial and or 1 over a polynomial, and we can easily find where the poles are of 1 over that polynomial, and we can then we can then determine what the residue is at those particular poles as well. Okay, that's all we have to say about this particular technique for integrating by residues.